Okay, so today we're going to talk about how to use von Neumann method to analyze linear stability of finite difference representation of differential equations. Last time, during last lecture, we derived the finite difference representation for simple advection scheme with constant speed. And we used upstream bias scheme for space derivative and earlier forward in time scheme for time derivative, and we demonstrated using Taylor series analysis that the scheme produces actually implicit diffusion term such that diffusion coefficient there depends on delta t and delta x on the time step and grid spacing in such a way that when certain condition is not on time step and grid spacing is not met, then this coefficient can become negative and produces negative diffusion. I mean diffusion with negative coefficient, and of course that's not only numerically, that's mathematically unstable. And but is there some general method to tell if a particular representation of differential equation that we use using finite differences, is it if it's stable or not? Actually, there are several methods for doing exactly that, but the method that I particularly like and that's pretty easy to understand is von Neumann method, although it has some limitations, but it's very simple method to apply to differential equations. Although it has this drawback that it generally cannot tell anything about stability associated with, say, certain boundary conditions. So this method is only applied to, of course, to linear equations, not nonlinear equations, and also it assumes that it doesn't give you any information about boundary conditions. It assumes that your domain is numerical domain is periodic, so it's there are no boundaries, and that's a limitation of this method. But still, it can be pretty useful in deriving stability conditions for numerical schemes. So this method uses stability of so-called Fourier harmonics. You know that any function can be represented, continuous function can be represented as Fourier series, like say some function f. F can be of x, can be represented as some sum of Fourier harmonics, well, not I, let's use M, such that it's complex exponent, because Fourier harmonics are sine and cosine, so this method, the complex numbers allow you to combine both in one function. That looks like that. So k and omega here are wave number and angular frequency for given harmonic m. So because it's linear, we can consider only one harmonic. We don't have to carry all this sign. Linear, I mean, because it's linear equation. So because solution is a linear combination of those harmonics with some amplitudes, of course. We can consider stability of particular harmonic, and then in some general form, and then if one of them, even at least one of them is unstable, then the whole solution is unstable. So it's enough to consider only one harmonic. So what's wave number? Wave number k is 2 pi divided by lambda, or wavelength of sinusoidal wave, and omega is a frequency, so it's 2 pi divided by period of a wave. And of course, those k and omega here cannot be arbitrary and depends on the differential equation, and they related to each other using through so-called dispersion relation. And this dispersion relation can be obtained by substituting these harmonics into differential equation and deriving some relationship between omega as a function, well, not this function, some function of k, and this is called dispersion relation. And it basically, so a wave of this certain wave number, certain wavelengths cannot have just arbitrary frequency. It can have only specific frequency omega. So that's for a given m. So of course it's the best to understand this using some example. Oh, by the way, this, just to remind you what this exponential is, this is earlier relation that exponent I omega equals to cosine, I alpha equals to cosine alpha plus I sine alpha. This is just the earlier expression. Alright, so let's say that we have some solution, we're looking for some solution to our differential equation, and it's in the form that some solution phi as a function of x and time equals to this Fourier harmonic, and we choose amplitude of 1, initial amplitude, and it's I, again kx minus omega t. So this is our solution, and this is just propagating wave basically. So that for wave, this is phase of the wave, it's conserved, so conserved along the propagation speed with propagation speed. So in order to find it, so kx minus omega t equals to some constant, and we can choose constant at t equal to 0. So it's equal to kx naught, initial position at time 0. So x naught equal to x at t equal to 0. And from that we have that kx equals to x naught plus omega divided by kt. So you see that this is speed, c, and from that we have the simple relationship that omega divided by k equal to speed of propagate of this wave. So this is dispersion relation too. So omega in this simple for the simple wave, linear wave, omega and k related like this. So if you have dispersion relationships of like omega equal function of k, then your speed equals to this function divided by k. So it can be function of wavelengths. Your speed in general may be function of wavelength. So now let's apply this to finite difference representation. So in our case, for finite differences, we have agreed so we have, let's use index m's because we kind of use here k here. M minus 1, m plus 1. So your x equals to m delta x, and we assume that delta x is constant. And time equals to n times delta t. So delta t is also constant. So if we substitute, we get that our grid representation or numerical representation of our solution in point M and time step n, so it's some time step n here, is phi m n equals to e I, where I is imaginary unity, so I square equals to -1. So I times times k m x, which is times m delta x, minus omega n delta t. So for given wave, omega is constant, k is constant, so it's just we may introduce new variable called lambda equals to e to the power of I omega minus omega t. Then our solution looks like formally as some part which is related to space, I k delta x times m times lambda in the power of n. So this one is not index n, is actual power of n. So basically the von Neumann method says that in order for the solution to remain bound, this amplitude, this is amplitude of the wave, it's or this, it's not quite amplitude, it's amplification factor, and it can be, it's of course complex number, right? So that's why we need to use absolute value. So we need that amplification factor, the magnitude of it should be smaller than 1. In that case, your waves will not amplify indefinitely unbound. When they amplify unbound, it means that they're unstable. So they can remain the same, or they may decay or being damped, and then, for that you need, so this is then that your wave is, solution is stable. So in order to understand how it's applied, let's apply it to our previously derived scheme, this upstream biased scheme. So let's try it. So upstream biased scheme, we have we're solving the advection equation. So we use upstream bias scheme with Euler scheme in time. So it has the following form. Use index m here now. So this is our upstream bias scheme. So now let's write it a little bit in different form, introducing this parameter mu equals to c delta t divided by delta x, and this is our current number, or CFL number, stability number, and using this number, we can rewrite this scheme as the following, that our solution at step n plus 1 equals to solution at step n minus mu phi m n minus phi m minus 1 n. So this is our scheme. It looks like this. So now we need to substitute wave, Fourier wave, and see if its amplitude would grow with time as a function or not, depending on this parameter mu, because that's the only parameter in this equation here. So let's substitute. So we have, instead of 5 this, we have lambda in the power of n plus 1. This is for this time portion. E, and we just use some alpha, this k delta x factor, just call it alpha. I alpha m equals to lambda power of n e to the power of I alpha m minus mu, and here factor lambda n is the same, so we'll take it outside. And here we have e to the power of alpha I alpha m minus e power minus I alpha, or alpha m minus 1. So now let's cancel some stuff. So we can cancel lambda n here. So which is left only lambda here. And also we can divide by factor e to the power of I alpha m, dividing both sides. As if you do that, we get lambda equals 1 minus mu 1 minus e to the power of minus alpha I alpha. So now we need to demonstrate. If you see, the lambda is a complex number because of this complex exponent here. We need to demonstrate or find out for which mu this lambda is smaller than 1, and because for some arbitrary mu it may not be the case. So we need to find out. So there are various methods how to solve this equation for. So what we need is to find if it's smaller than 1 or equal to 1. Actually, it should be equal. And if it's the case, then solution will not amplify with time. It may remain the same if it equals to 1, or it's the same amplitude, or it may decay with time if lambda is smaller than 1. But as long as it's kept smaller than 1, solution will be stable, linearly stable, because we consider linear equation. So how to solve this? Of course, you can write definition of exponent as a sine, cosine. You have a complex number, so lambda is a complex number. Z, usually like complex numbers like denoted as Z. So it's some real part plus imaginary part times I. And we want that lambda amplitude, then it will be equal to what? It will be equal to a square plus b square square root of that. Then it should be smaller than 1. And of course, because it's smaller than 1, that you don't really need square root, because any number which is smaller than 1, square root also will be smaller than 1. So for positive number, and so it's just enough to find a real part of the number of this complex number, imaginary part, square them and add together, and then see for which mu, solve it for mu, and see for which mu it's actually this condition is satisfied. So it can be sometimes very tedious process, and for this particular scheme, this process is pretty tedious. Even though the scheme is very simple, the equation is very simple, but showing that using just cosine and sine functions is pretty tedious, and so I will not do that. And instead, I will show you using graphical way how you can solve this equation, just using graphs. Okay, so let's consider this as an example. So we have function, so our complex number lambda equals to 1 minus mu, 1 minus e minus I alpha, and we want that its amplitude is smaller than 1. So let's see. Let's little bit remember our complex numbers, educational complex numbers. So we have here we have imaginary, here we have real numbers. So we have so what's what we want in terms of lambda. So this is 1 minus 1, 1 minus 1. So this is what we want. We want our lambda to be inside of this circle, because so amplitude of a complex number is, of course, this is your complex number z, and amplitude is just length of this. So this is cosine portion, this is your sine portion of a unit vector. So we want this lambda to be inside this circle. In that case, this condition that lambda, amplitude of lambda smaller than 1 will be satisfied. So okay, let's do it. Let's plot this function. Just to plot. Okay, so we have again 1 minus 1 minus 1 1. This is imaginary numbers here real. Okay, so what is e to the power of minus I alpha? How it looks like? Well, it's just cosine plus I sine, so it's a unit circle with a center at 0. Regardless if it's minus or plus, it's just plus would rotate like, say, this direction, and minus would rotate this direction, but it's still in the same circle. So it will be circle, the center in here, and it will be like that. So this is our function of e to the power minus I alpha. So now, and plus or minus, it in this case it doesn't matter, because what minus does? Minus to complex numbers flips it like along this axis and along this axis. So this point becomes this and this point becomes that. But in this case, because it's symmetrical at 0, minus sign doesn't change this function at all. It's the same function. So it stays here. So minus or plus doesn't matter. Now, adding 1, we need to add 1. What 1 is? And this is a real 1, not imaginary. It's real 1. It will shift our circle to the right by 1. So it will be now centered at 1. Here is 2. So our circle will become this circle. So this one is 1 minus e minus I alpha. Now it's multiplied by mu, and minus sign applied. And what's minus sign applied? It means that this circle should again flip. If you flip it along around real axis, nothing will change again, right? It's the same circle because it's sitting right on this axis. But if you flip around this, it will actually become this circle with centered at -1. So this one is now becomes -1 minus e minus I alpha. And of course we multiply it by mu, and mu can be from 0 to whatever. It's positive number, but it can be anything. So for some arbitrary mu, we conclude that this guy, this is your minus mu, 1 minus e minus I alpha, this circle. And now we add 1, which means that we now, in this circle, circle is arbitrary radius, it can be anything. I just plotted it like that. But now this circle should be, we should add 1 to it. It means that it will shift by 1 unit along this axis, because it's a real number. So it will go there and will become this circle. Right at the center again. So we went all this kind of, by using these operations, we arrived to this 1 minus mu, 1 minus e minus I alpha. This is what our lambda is. This circle centered at 0. Of course it's accidental, it's not always like that, but in this case it is. And so we need this radius, and this radius of this circle is actually mu. Because we multiplied by mu. So in order for this circle to fit inside this circle, which is stability, this is stable, we need that our radius would be smaller than 1, which means that from that we have conditions that mu should be smaller or equal, if it's right on the circle, than 1. And then from that, lambda absolute value is smaller or equal than 1. It's guaranteed. So our stability criterion for upstream bias scheme is the same as we got before in last lecture, that mu equal to c delta t divided by delta x should be smaller or equal than 1. And then the scheme is stable. So it's very neat. I kind of like complex numbers a little bit, although they're a little bit confusing sometimes, but using these graphs sometimes can be pretty helpful. And much easier than tedious work of deriving this using sine and cosine functions. Although sometimes it's not that bad. And for that, let's consider another example. Diffusion equation. It's in one-dimensional diffusion equation. It's in the following form. The time derivative equals to diffusion coefficient, second derivative of 5 divided by second derivative, and new diffusion coefficient. So we will use again Euler scheme for time. So this is our transition to algebra. We have phi m n plus 1 minus phi m n divided by delta t. So this is our Euler derivative, finite difference representation of time derivative using Euler scheme. So it's upstream, Okay, so it's just one step, two level scheme, and it's equal to nu. And here we need representation for second derivative, and we derived it before when we talked about derivatives, and its most common one that used for this kind of diffusion operator. It's 3-point scheme. So we have phi m plus 1 n minus 2 phi m plus phi m minus 1 n divided by delta x squared. So this is centered in space and forward in time representation of a diffusion operator. So we basically could plot some kind of pattern. So this is space, m minus 1, m plus 1, and here is time. So this is n, this is n plus 1, this is n. So for this scheme uses this kind of pattern. Okay, so let's rewrite it a little bit more in a friendlier form by introducing mu. In this case, mu is different. We use the following thing. It's nu times delta t divided by delta x squared, so that we don't have to carry all these delta t's, delta x's around. It's much easier to carry mu. So we can rewrite in this scheme as phi m n plus 1 equals to phi m n plus mu phi m plus 1 n minus 2 phi m n plus phi m minus 1 n. So this is very compact and nice form of our finite difference representation of this equation. So now we need to find if our Fourier harmonics grow or not given particular choice of mu. So we need to find some condition on mu so that our harmonics would not grow, that the amplitude would decrease with time at least, or not growing. So let's again substitute our harmonics. So we have n plus 1, so it's lambda power of n plus 1. E, here it's I alpha m equals to lambda n E I alpha m plus mu. So we take this lambda n outside, because here they're all n's. Lambda n. Here we have E I alpha m minus 2 m plus 1 minus 2 e to the power I alpha m plus e minus I alpha m minus 1. So now we divide both sides by lambda to the power of n as before, and also by this factor e to the power I alpha m. Then we'll get that lambda equals 1 plus mu e alpha I alpha plus e minus I alpha minus 2. So now what's this? Remembering that e to the power I alpha, earlier identity, cosine alpha plus I sine alpha. So e to the power minus I alpha, because cosine is an even function, so it remains cosine alpha, because cosine of minus alpha equals to cosine alpha, minus I sine alpha, because sine is actually changes sign if you change sign of alpha. So now if you add this to that, from that, you see that cosine will remain and sine will cancel. So we have that lambda equals to 1 plus mu times 2 cosine alpha minus 1. So now we don't have any imaginary unit, so we don't, this one is real equation. So it makes it a little bit less fun using these complex diagrams, but it's simpler to deal with. So from that, if actually I will leave it for you as an exercise how you do it. Well, maybe I should do it one time. Let's see if I do it here. So it should be smaller than 1, absolute value. So now let's see. In order for this guy to be smaller than 1, this is absolute value, right? You need that this guy inside of this should be in the interval from 1 plus 2 mu cosine alpha minus 1 should be smaller than 1 and should be larger or equal than minus 1. It's equal. Then this guy absolute value will be less than 1. Okay, so cosine interval, cosine alpha can be from minus 1 to 1. So, and mu is greater than 0 by default. We assume that it's greater than 0 because by definition that our diffusion coefficient is greater than 0, so everything is greater than 0. So mu is positive. And so cosine can be positive or negative. So now this guy, if it's it can be if it's let's first check negative values. So if it's minus 1, negative 1, then this guy becomes negative 1 minus minus 1. It's negative 2. So it's 1 minus 2 mu plus times negative 2, and so you subtract from 1 this guy, and so this guy in that case should be smaller than 2 because 1 minus 2 is negative 1. So that's one case. Another case, when cosine alpha equals to 1, then this guy becomes 0 and then it's 1. So because cosine is in this interval is changing like only in this interval, so it's enough to consider this kind of bound cases because it's kind of linear function of cosine here. So from that we the only condition that so for a cosine alpha equals to 1, everything is satisfied automatically, and for cosine alpha equals to negative 1, we need that 2 mu times negative 1 should be smaller. I mean 1 plus 2 should be smaller than 2. Oh, sorry. So this guy should be is positive. Should be smaller than 2. Then you will subtract 2 from 1 and get negative 1, and then it's fine. So what you get here, you have 4 mu smaller than 2, or mu smaller than 1/2. So when equal. So when mu is smaller or equal than 1/2, this condition is satisfied, and scheme is stable. So for diffusion, we need mu equals to nu delta t divided by delta x squared should be smaller than 1/2, or your time step should be smaller than 1/2 delta x squared divided by nu. Then the scheme is stable. So what we conclude from that your time decreases as quadratically. I mean, if you decrease your grid spacing by a factor of 2, your time step would have to increase for the same diffusion coefficient by a factor of 4 for the scheme to remain stable. That's not good news. That's relatively bad news, because you basically increase your resolution, and then your time step should decrease even more than your resolution. So and that's not good. So you will have to simulate the same time. You need to make your time steps 4 times smaller if you double your halved your grid spacing. And also, if you have very strong diffusion coefficient, you see that your time step also will decrease considerably, but kind of inversely proportional to it. So near the surface, for example, if you use it as a diffusion away from your surface, the diffusion coefficient can be very large. Like I'm talking about so-called turbulence AD coefficient that we're going to talk about when we talk about parameterization of turbulence in models. But this one is kind of coefficient which is computed by the model, and near the surface it can be particularly large. And as a result, your delta t can be particularly small. So just few grid points near the surface may dictate what time step you should use for the whole domain, because you cannot choose specific time step for specific point. As I mentioned before, you need to use it like for the all points. So several grid points can actually slow down the whole model quite substantially. That's why for, say, vertical diffusion especially, because usually grid spacing is much denser in the vertical direction than horizontal, at least in our models. That means that you probably need to consider some other schemes that are not less restrictive than this one, than this centered schemes that we talk about here. And we're gonna find some schemes that actually don't have this restriction at all, so-called implicit schemes. Okay, so that's another example of stability analysis using a Neumann method for this case of diffusion. So now let's maybe consider one more example of a scheme which is kind of popular scheme in certain models. For example, in WRF, or not maybe in WRF, but in the past it was, and it still is actually pretty popular scheme called so-called leapfrog scheme. And so let's consider one more example. In this case, it's a improvement scheme over our upstream bias scheme relative to upstream bias scheme. Last time we actually talked about the fact that earlier scheme in time combined with centered differences, second order approximation of the first derivative, produces unstable scheme. What I'm talking about, so if we use, again, we return to our advection scheme. So this is advection equation, and our upstream bias scheme, not upstream bias, centered differences scheme. So if we use the following scheme, phi n plus 1 minus phi n divided by delta t, and equals, now here, instead of upstream bias scheme that we just considered, we consider center differences, which is second order accurate, unlike upstream bias scheme, which is first order accurate. So we'll consider scheme like m plus 1 minus phi m minus 1 n divided by 2 delta x. And last time we mentioned that in this case, this scheme is unstable. It will blow up no matter what, regardless of time step you use. Can we show that using our new method? Let's try it. So let's rewrite this scheme again in our form. So it's lambda n plus 1. And I won't write this exponent there because it's kind of, you probably by now already learned how to do it. So because and so I won't write n here too, I will already cancel by lambda. So lambda equals to 1 minus 1/2 mu, our mu that we used before, current number. Here phi m plus 1 minus phi m minus 1. Not phi. Exponents e I alpha minus e minus I alpha. So if we apply our method to this equation, this is what we'll get. So now using our cosine sine kind of Euler identity, we can simplify this as lambda equals 1 minus. So cosines will cancel, which is remain here is sine. So minus 1/2 I mu, and here is 2 of them, so 1/2 will cancel. So mu sine alpha. So what we see here, this is our equation. So we could square it, find real part squares, and imagine in this case it's not that tedious, and then add them and get our equation. But let's also use again our fun way, which is using diagrams. So this is real, this is imaginary. 1 minus 1 minus 1 1. So what's this guy? This is all truly imaginary function. It's just imaginary sign. So it's this guy is somewhere along this axis. So depending on mu, it can be different amplitude. So it will oscillate like that along this axis. So this guy is mu sine alpha. So it's plus or minus it regardless. It's the same. It doesn't change if you change the sign. So this is function that we have, and then we add 1 to it. So what we do by adding 1, we shift it to the right by 1. So now it's here. This is our function, so this is our lambda. But our lambda should be within the circle for stability. But it's right outside it, or just touching it here. You see, it's outside the circle. It means that there is no such lambda which amplitude is smaller than 1. You see, it's outside of this circle when amplitude is smaller than 1, which means that this guy is unstable. Yeah, I kind of like this type of diagrams because they're much more, I think it's way easier to apply than just direct method. Not always, but in this case it is. You can actually write computer programs that would plot you diagrams like that, given like equation. So that's why this scheme is unstable. So it's garbage. Unfortunately, because that would be a really cool scheme if it was stable. That's what would be really great. But it's not. So how to repair this scheme? This scheme can be repaired by doing the following. By considering not 2-level scheme, but 3-level scheme. So this is centered differences in time, and this is centered differences in space. So this is so-called CTCS scheme. So centered in time and space. So this is three-level scheme. And also because in a way, like if you have these levels here, this is x, this is time, so you have solution here equals to solution here, like this minus this solution, and this is right hand side and this. And then on next time step it's actually kind of going like this, so you're basically like going like that, you kind of jumping over one level to the next one. So from this level to this level, using this kind of as your anchor or your support, and then you keep jumping. So that's why it's called leapfrog scheme. So let's analyze this scheme. So let me write. By now you already understand how to do that. But here, because we have three levels, we have actually now quadratic equation for lambda. So we have the following: lambda square minus 1 equals minus mu. Oh, let me write already. Cut it to the chase. So it's lambda square plus 2I mu sine alpha times lambda minus 1 equals to 0. So now it's a little bit, so you see these coefficients, this is quadratic equation with respect to lambda, and coefficients are complex numbers. So here's imaginary number here. But it doesn't matter. You solve it the same way as you solve ordinary real kind of quadratic equation. So the solution is written as lambda equals minus b, which is in this case, minus 2 alpha I mu sine alpha. Let's call sine alpha as sigma, just for brevity, for the sake of brevity. Yes, and now plus minus discriminant here as b squared. So b squared, because I squared is negative number, so it becomes negative, minus 4 mu square sigma square minus 4ac, which is minus 1 and 1, so it's just plus 4. Divided by 2 divided by 2a, which is by 2. Okay, so this is the solution of quadratic equation. So now let's see. Let's first divide by 2 both sides. So we get just minus I m nu plus minus square root of 1 minus mu square sigma square. So for this thing, so sigma is from minus 1 to 1, so it's amplitude. So this is complex number. And this one is 1 minus something, but it's a real number. So this guy, and you're working with this guy. And in order for not to produce another imaginary number, this guy underneath this thing should be kept smaller than 1, which follows that for that, it's actually condition for that this should be smaller than this thing should be smaller, I mean greater than 0, also means that smaller than 1. From that it follows that mu should be smaller than 1. But now if you make a lambda square, you will get that it's mu square sigma square, because this one is imaginary plus the real part, so that's why you needed to keep it real, this condition. Then you have plus 1 minus mu square sigma square, and it's equal 1, because those two guys cancel. So provided this condition, lambda is 1 for any harmonic. So stability criterion is still the same as before for upstream bias scheme. But unlike upstream bias scheme, this scheme does not have damping property on a solution due to diffusion, this implicit diffusion. Remember, in upstream bias scheme, we have this implicit diffusion term, which is hidden from us by finding different representation, but it's there. And diffusion always tries to smear things out, reduce amplitudes. And this scheme doesn't do it. It actually preserves all amplitudes the same. They all stay the same, as they should. Because actual true solution to this equation, amplitudes are preserved, because this equation all it does just transport stuff along the x-axis with velocity c. It doesn't really diffuse or damp anything. So this equation, and this explains why this scheme is it has been so popular among modelers, so-called leapfrog scheme. It's because of this property. But it has some other bad properties that we're going to talk about some other lecture, that so-called computational modes or artificial solutions that don't actually exist in this scheme. So it basically generates some computational signal mode which actually travels in opposite direction. So instead of traveling in this case to the right, there is some computational mode that actually travels to the left. And it's because of this staggered nature of this scheme, because of this leapfrogging. So it generates two sets of solutions that don't actually talk to each other. And you need to use special filters that connect those two solutions and damp computational mode. And in that case, this scheme is pretty usable, and that's drawback, that not a good property of this particular scheme. It's one of the reasons I don't like the scheme myself, because it's too tedious to me. I like to use some schemes that slightly damp, or at least damp the computational mode. And we're going to talk about that in some other lecture. But nonetheless, this scheme has been popular because of this property. So it's not diffusive. So but it's dispersive nonetheless, and we're going to talk about again in another lecture what it means. So I think that's it concerning using this linear stability analysis with von Neumann method. I think it's very nice method, very simple, and it produces immediate results. You can immediately say if your scheme is unstable or not. Sometimes, again, I need to stress that this analysis is to linear scheme. Linear means that this coefficient here is constant. If this coefficient is a function of x, it's or function of like phi itself, that's more precise. Then, which is the case in our field, because this is usually, say, advective operator. For scalars, it's u here, which is actually changing with time and space. And for momentum itself, for u itself, it's the same equation. So it's nonlinear. So our equation is nonlinear. And yet we do this stability analysis for linear equation, and you may ask how relevant is it to actual equations that are nonlinear differential equations. Well, that's a hypothesis that even though you have this nonlinear, that scheme to the first order behave like linear if your velocities don't really, pretty like relatively smooth functions. So in practice, what you do if you have actual, so for equation which is like looks like that, so instead of constant c, now it's a linear equation. Then you use your criterion like the following. You assume that your delta t should be smaller than maximum velocity on your grid, maximum of all m of your um times step n, say, it's delta x divided by maximum absolute velocity m n on your grid m. Instead of using just c here. So basically you take the worst case scenario, the fastest velocity on your grid, and then you derive your time step for the next time step, for the next step of your model run. And in that case, this is usually works all right. So you need to, maybe you need to get a little bit, some safety margin, say 0.9 before in front of that. 90% of your required. But usually that will be all right condition for stability of your nonlinear scheme as well. Of course, nonlinear scheme have their own instability that we're going to talk about some other lecture, called so-called nonlinear instability, which is completely has nothing to do with this. And it's very scary and spooky phenomenon that sometimes occurs, and it would come sometimes seem like coming from nowhere. It's so-called nonlinear instability, and we'll talk about that later. But in practice, you use your analysis for stability using constant velocity, and then just in actual model run, you replace that constant velocity with maximum velocity on your grid. And then this becomes your stability criterion. Okay, I think that's enough for today. See you next time.